All right, we're right at the start time of 12 o'clock Eastern Standard Time, so we'll go ahead and begin. First off, good afternoon. My name is Jason Thomas, and I'm a project engineer here at the National Center for Defense Manufacturing and Machining. And I'll be your host for today's NCDMM Alliance Partner Lunch and Learn. NCDMM has established a team of over 200 alliance partners who provide significant manufacturing expertise and technology as leaders in developing, researching, and enabling manufacturing technologies. This collaborative approach to developing and deploying best-in-class solution is successful because we integrate the specialized and innovative skills, technologies, and practices of our alliance partner network. If your organization is interested in becoming an alliance partner, you can navigate to ncdmm.org under Who We Are, and you can click on Our Partners. Or you can click on the link that I'll be sharing in the chat here, and there you will find a link to submit your application. So let me go ahead and drop this in the chat for you. All right, once again, if you're interested in becoming or researching alliance partners, please follow the link that I just dropped in the chat. A few important notes before we do kick off the Alliance Partner Lunch and Learn. At the end of today's presentation, there will be an opportunity for a question and answer session. If during the presentation you do have a question, please submit it into the Q&A space on your Microsoft Teams screen, and I'll ask it during the Q&A session. I will do my best to get all of your questions answered. Today's NCDMM Alliance Partner Lunch and Learn is focused on real-time certification with in-situ inspection. Without further ado, it is my pleasure to introduce our speakers, Noah Mostow and Ben Ferrar. Noah is the Business Development Manager at Phase3D, is passionate about additive manufacturing and advancing the industry through his work. During his career in AM, Noah has worked at companies including 3D Systems, Wohlers Associates, and ASTM International. He has spoken internationally at industry events and has been published in the Wohlers Report, Metal AM Magazine, and SME Magazine. Noah joined the Phase3D team to push the boundaries of AM using Phase3D's patented technologies that he believes will change the AM industry forever. Ben is the chairman of the board and chief operating officer at Phase3D, where he leads the commercialization of advanced quality assurance technologies using fringe projection to ensure superior part quality and additive manufacturing. With 17 years of experience, Ben previously served as vice president and general manager at Carpenter Additive, enhancing the company's global leadership in additive manufacturing solutions. As a chief operating officer at LPW Technology, he drove sustainable growth and led investment strategies for a 20 million digital factory. Additionally, Ben has been a liaison board member at the University of Liverpool, and his expertise in corporate finance, board governance, and the industrialization of additive manufacturing technology underpins Phase3D's mission to provide trusted and high-performance solutions to the industry. Noah and Ben, I'll now turn it over to you and your team. Go ahead and take it away.
Yeah, thanks very much. I'll start and I'll get into the business model side of things and why it's so important to be doing in-process inspection and some of the value that is created. And then Noah will take the presentation and go into a bit more detail about our products and give you some demonstrations of the capabilities. So I want to start off by showing you a video and perhaps asking the question, what's happening? So if you watch this video, okay, you can see that so what this image is it's a laser traversing across a powder bed, and then using an X-ray synchrotron, we're looking at the cross section and we're seeing what's happening with the melt pool and also with porosity formation. So this was done in Ti-64, and we deliberately seeded some defects into the powder bed. So on the left-hand side, you can see that the powder bed is slightly thinner, and on the right-hand side, you can see it's slightly thicker. And really that correlates to about a 50 micron depression on the left-hand side and about a 30 micron protrusion on the right-hand side. You can see that where there's a depression in the powder bed, it causes a significant amount of instability and ultimately creating large pores. And on the right-hand side, you can see a huge amount of ejection of powder particulate and a much more unstable melt pool as well. So, when we look inside an AM machine, it's very easy. You don't need to play it again, Noah. You can click onto the next slide if you'd like. So when we look into an AM machine, it's very easy to see, the laser moving, but you have to ask yourself the question, are we really seeing everything that's going on inside the build chamber? And when an engineer sees either a part protruding out of the bed a tiny bit and it causing some small amount of streaking, what is the magnitude of that and what's the potential impact of it? And it's something that we've been working really hard on at Phase3D to really understand the relationship between what happens during the printing process and final part properties. So we'll discuss that in more detail as we go through the presentation today. So firstly, let's take a big step back, right? If we think about where additive manufacturing is, and many of us that have been in the industry for a while have been saying it's in a pivotal phase, for what feels like a decade. But really ultimately the applications that have won in the last 5 years and have fueled the start of the growth in production have been based on adoption of geometric freedom. So a lot of heat exchangers or other, cooling channels or fluid flow for aerospace and defense. And then in the medical industry, yes, we have the customization aspect, which has driven a lot of the growth, but also the unit cell structures that enable bone growth have really started to shape the growth. And you can see an image of an enlarged porous structure at the top. And so when we ask ourselves the question, what do you need to be able to do during additive manufacturing to actually enable those really fine geometric structures and internal structures, you have to be able to ultimately validate what you've built, right? And so one of the things that we're really proud of our technology for is because we're taking measurements during the building cycle, we can actually validate that features have been built, measure features that are inside a structure that can't be measured any other way. And that's why we see so much CT scanning today in additive manufacturing for part validation. So we see this as the next step to unlocking the future in additive. If you want to move on, Noah. So we talked a little bit about from a geometric point of view, but let's think about it from a qualification or quality perspective. A lot of our customers today are seeing high scrap rates, and many of these things are caused by issues that are happening in the process that aren't necessarily repeatable build to build. So they might run a build once and they might see a certain number of anomalies in their layers or parts that start to flick up or protrude, but really it's very, very hard for them to validate. And for us to make the big shift from the $6 billion market today to the production market in the future, we have to improve our quality standards. And to be able to do this, we have to be able to quantify what those standards are to get to production. I'm going to flick on. So, we see Phase3D's Fringe Inspection technology as critical in the future to enabling quality and ensuring reliability. When we think about how much data we take from a manufacturing process, today we're taking a huge amount of data before a build process and after a build process in terms of tensile bars, metalographic samples, and before we're doing a lot in terms of simulation and topology optimization on designs. But really the missing piece is what's going on in the build platform. And there's a number of qualitative methods that are being used. People can look through images, but we see fringe inspection technology as being the first real method to quantify in process what's happening. So if we look at the cost of a build going wrong and you're not seeing it, and just to explain where we are today, right? Most OEMs who are manufacturing parts with a subcontractor or even internally will specify in their part spec that every layer must be reviewed of a build. So you have all these engineers around the country and in these big print farms reviewing the most boring video of their life where they watch a build and they qualitatively say, oh, it looks like something's sticking up there, or it might be a streak, right? And ultimately then they have to get into a discussion. Okay, well, can we accept that, or is the part sticking up too far? This causes what this generally means is for the lead times, they miss defects. So these things will happen during the printing process. The parts will continue on their route through a production facility, go through post-processing and inspection, which can be very expensive with, heat treatments or HIPs or machining and post-inspections like CT scan. And then when they get to the end of it, they have to restart the build because they've reviewed the movie, or they've eventually got to the point where they've figured out or agreed with their customer that it's the defect that they see is not acceptable. What our technology allows is during the build, because we're quantifying during the build what's happening to the bed, our customers are able to set limits in terms of what they'll accept. So if they say, look, if there's over a part sticking up over 200 microns, we know that we're not going to be able to accept this. So kill the build and restart. They save both the lead time and the cost. And these costs can be significant. So if you move on to the next slide, Noah, if we take a part like this example here, which is a heat exchanger, the 3D printing cost was about $14,000, and the total cost of post-processing and post-inspection was $25,000. So if you don't catch these defects or internal geometry issues early, you're liable for that cost. So with our technology, if you're able to save half the build time and all of that cost of post-processing, it's a significant improvement of CPQ, cost of poor quality. Okay, so I talked briefly about all the information or data that we're gathering pre-print and what we're capturing post-print. And a lot of the data that we're capturing today during the print may be, either really low resolution information or not really good leading indicators of what's happening in the process, like things like oxygen content or temperature or other environmental conditions. But with our technology, we enable that quantifiable data to be created during the print. So Noah, if you want to click on. So we can start to understand, okay, well, what did the printer do? Was there short feeds? Was there protrusions? Was there recoater impact? Was there any lack of fusion? Or all of which our technology has the capability to do in the future. It really becomes a question of resolution and time, right? How long do we want to take taking the measurement? So with that, I'll hand over to Noah to talk to you about in a bit more detail about our products and how they work, and give you a demonstration of the software.
Yeah, so thanks, Ben. Today I'm going to really focus on really what we're doing and how this can impact you all within either your facility or the customers that you work with. So at Phase3D, I'm going to pass through those slides. Ben, I think those are still yours, but I think you covered all the topics. So at Phase3D, our product, Fringe Inspection, really is based around fringe projection. Now, many of you today probably have seen 3D scanners, whether it's walking through your facility or walking through an event. every single year. Our technology, Fringe Inspection, is based off of what is happening today or what is happening within the machine using fringe projection. So what we do is we mount a camera and a projector outside of the build chamber, and then within it, we're projecting a fringe pattern, which is basically a sinusoidal wave that identifies where there's a variation. Now, we're not going to get into the mathematics of fringe projection today. If you are interested, I can send you a lot of really fun scientific papers about how our technology is working and the backbone to it. But what you need to know is basically how our eyes work. It's very similar. We have a distance between them, and what we're looking at is a variation. That's how we can tell depth. So our technology itself does this in really quick time for the entire build area. So we can go into the math around how it's doing, but what you need to know is the camera and projector are working together, and then we have a calibration surface that is based during setup and then routinely updated so that everything is uniform. And what you're seeing here for this shape popping out, this is really what you can see. When you're looking into the build with a fringe pattern, you're able to see variations because we're making and controlling a line or wave. That is what allows us to take that measurement. And this is different than any other in situ monitoring technology in the industry. And that's really why we consider ourselves inspection, because we're quantifying it. So what does this mean? Now, many of you today probably have seen build images, or if you've looked into a metal 3D printer, it's a relatively flat surface. And what you're looking for in the visual spectrum is you're looking for a shadow to identify a problem. This isn't good because really it's subjective. We can go back and forth all day and argue about what does this mean? This is a hot pattern, but is this something that we should fail to build? What we do at Phase3D and what our output is a height map. So every single pixel is a measurement and we're quantifying what's happening. So now we're able to create thresholds that cause build failure, and we're able to know and tell our customers what to do based off of a unit measurement. Now today this can look like root cause analysis for build failure, which we'll get into all the way into failing parts. In the future, where we see ourselves is a certification technology. Now this is because we're able to quantify. And even beyond that, our core technology has these kind of 5 pieces. So we're not using artificial intelligence or machine learning to identify these anomalies. Now, many of you on this call probably have used ChatGPT or Claude or whatever AI model to write an email. That's great, but that's not an inspection technology. We can't trust a black box to say that this part is good because we don't really know what's happening. For my background, I'm an engineer. So I've created neural networks when I was at the Colorado School of Mines, and having created them, let me just say, you can't trust them completely. And because we have that unit-based, repeatable, calibratable, known uncertainty measurement as the backbone to our technology, we're able to really understand what's happening and make decisions using really objective measurements. And this is where we differentiate ourselves from others in the industry, because you're not questioning, is this a protrusion of X amount out of the build? We know, we can tell you why we know it. So our technology, Fringe Inspection, takes 3 measurements per layer. So what does this look like really when you're running a build? We take a measurement after the powder is spread. We take a measurement after the powder is melted. And then we also take a measurement after the build area repositions itself. Now this allows us to quantify exactly how much powder is spread across your entire build area. This is something that is actually a feature that came off of a customer request because they were trying to do this for years, taking out the build plate, putting it back in. But because we're taking these unit measurements, we're able to take a delta. So we know how low the build area has repositioned itself and then how much powder is spread on top. Now, this has really been changing our customers' perspective on what's happening. You may think a 30 micron layer is spreading 30 microns of powder over your part. Really, what we're seeing is it's spreading up to 200 microns. And we'll get into an example here in a second. We'll pull up data. But this is really where we're looking. Now, additionally, for our technology, we do have measurements. So X, Y, Z measurements. And these have resolution and repeatability. For these 100 microns and 10 micron specs that we're pointing out here, These are for a standard EOS M290. And if you're interested, we can get onto a call and go into exact specifications of our system, where we've done all the research behind it, really the engineering, so that you know what the measurement output is. Again, this is where we differentiate ourselves because it's an actual measurement. We're not just giving you a gray value or your black box saying that it's good or bad. You can know what's happening. So what does this look like? Ben talked about some of these anomalies that you may be detecting. Here, I just kind of took some screenshots of builds that we've run where we can see different anomalies. And what you can really think about this as is when you're printing, if there's a variation on the top surface of your powder layer, you're going to be able to not only identify it using our technology, but be able to quantify it. And that gets into what we'll talk about here in a second, but thresholds. So just to kind of run through these recoder streaks, maybe the build was lifting up, hit the recoder blade, drag some metal through. Aha, the part was lifting up, it actually jumped, and you can see and measure the reverberation over the entire build. Know is it going up or down? Short feeds, bigger problem than it should be, but we still identify them on almost every build. Part protrusions, powder dropping is a really interesting one that personally, when I started the company, I didn't know this was a problem. And this was a key challenge for one of our core customers who powder was dropping onto their part and it wasn't repeatable. And that's one of the challenges with additive is every single build is not the same. And I'll show you a fun example here in a bit. And then we also, because we're taking measurements after the powder has been melted, spatter particles, powder redistribution, the laser is almost plowing powder forward. And then also looking at the hatch pattern, which is really interesting as we start to look at multiple lasers and looking at stitching patterns. Just for some examples, there are others as well. This is the ones that could kind of fit in this slide. But let's start to talk about what you actually do with this. So this slide here is telling you a little bit of a story. What we've done with our customers when they really adopt our technology is the goal here is to be able to stop a build. So what we'll run through is a design of experiments where we're printing anomalies or printing parts that have anomalies that are going to impact the part, measuring the entire process as we've discussed, identifying what defect or flaw occurs within the part, and then we want to control the entire process. Now, this is all dependent off of your specification. So whether you're looking at CT scanning or you want to be doing fatigue testing, tensile bar testing, this defect or anomaly to defect, excuse me, is really that key challenge. So how do we correlate the two is some of the work that we're doing on a day-to-day basis to be able to understand what is really causing the part to fail. Now, I'm going to be upfront with you. I would love to be able to say, this anomaly causes this part to fail inspection. But that's not how additive works. If you're printing bottle openers, you can have all the anomalies that you want. All that you care about is does it open the bottle at the end of the day? But if you're printing a part that's going on to an aircraft that's spinning, you have a lot higher of specifications and even different specifications per region. So that's where we can start to do this work and create different build profiles. And really what we're looking at here is improving the process based off of that profile. So what is a go, no-go criteria? Because at the end of the day, we're manufacturing. And this is a key piece to know is we can't be continuing to look at this as, I have 30 years of experience and can listen into the machine and know that's going wrong. No, we need to be quantifying. And that's what our technology is doing. So some of the work that we can publish here about these correlations is for the US Air Force, which this work was done on EOS M290 using TIE 64, as well as for NASA using GR-COP on an M2, equilibrium additive M2. Now you can see a high correlation for both of these studies from the anomalies to detected CT detected defects, but also we want to look here that we actually were able to see the same amount of comparison of 50 micron anomaly depression led to a pore that was detected in the part, which we need to continue to do additional studies, and this is what we're doing with customers to know what is this universal, what's happening. We do see this at other customer sites, but for each different parameter set, material supplier, we want to make sure that everything is happening correctly. Now you may be able to say, okay, great, but I can identify anomalies using the camera that I have today. I'm going to challenge you on that because in reality, you're missing a lot. As I mentioned before, a camera is looking for a shadow. So depending on where your lights are, you may not be able to detect the anomaly at all. So this is an example where in the visual spectrum, and we're really zoomed in here, these are about an inch by an inch apart, you can't identify any anomaly. For us, using our height maps, it was easy to detect a recoder streak. We're able to see it going through the part. And then that recoder streak does impact the porosity or the density within the end part. Now, this was all detected, and this is a part that was done. This is one of the NASA parts that we pulled out. And what's amazing here is just what you can't see versus what you can detect using fringe inspection. Because this is what's really going to change the industry in our mind, is we can't keep relying on people who've run these machines for years. We need, in my mind, in our mind, we need to be able to have anyone who comes on site be able to run the machine, know when to stop it, and then be able to provide educated information on that part all the way through the process chain. And that's how we reach born certification, is by knowing what's happening in the machine itself. Now I'm going to get into here in a second, but what I want to kind of describe is our product suite. So Fringe Inspection is really what our product is, and product suite allows you to take the measurement. Now then we have two options here. We can either get into Fringe Operator, which is your analysis, data visualization, which I'll show in a second. And then we have Fringe Qualification. This was released here at Formnext, and this is your high-level overview of the data that you're gathering at your facility to know what's going on. Now, all of this work, we can't forget to thank all of our partners and all the work that's been done. We've been working closely with the U.S. Air Force, Department of Energy, as well as NASA, as well as a bunch of private customers as well. But really, all of this work is being done to gather the information to continue to advance the industry itself. So let me switch here. We're going to kind of switch pages and look at Fringe Operator for a second. So Fringe Operator, this new screen that you're seeing here, this is a tool that is on a computer next to the machine. It can be at your desk. I'm running this off of my laptop here to do data analytics and analysis. And we have a few different pieces within this tool. The first one, what we kind of call the heartbeat plot, the quality chart, we're looking at the volume of anomalies as the build grows. So you can see different peaks, what's occurring within it. I kept kind of pulled up this large anomaly prop or area that we can take a deep dive into. But also within this, you're looking at the anomalies within a table format. And this is important because you want to look at the biggest one first. Let's fail early so that we can know what's occurring. So we can go exactly to a layer, which is, well, that's great. Going to go to a layer with a different anomaly to know what's occurring. Weird. Let's go here. Oh, because they are small. So I'm just going to go back to the heartbeat. It's what I've been using the most. It's kind of the easiest one for me to travel around for. So looking through it, we also have a 3D visualization to understand what anomalies occur in real time, so that these are streaks as well as hops automatically detected. We're continuing to grow these filters to be able to detect other anomalies as well. And then the final piece here is really that data analytics tool. 2D analysis to understand what's happening in real time. So as a notification or anomaly occurs that's greater than your threshold, you can go in and understand what is really happening in this layer. So if we want to look at the powder layer, we can see what's happening, but we're also taking a melted measurement. And this is showing where the part is, what it's impacting. Maybe for this layer, this is just where support structures are. This isn't really going to impact anything. But we can also detect this short feed and quantify where it goes to the part itself, how it's getting impacted. Now, a layer that, or a measurement that I always like to kind of look at is true layer thickness. This is what is quantifying exactly how much powder is spread across the area, as I mentioned before. So if we're looking here, we can see a lot of powder was spread across in this region. The part itself is a 30 micron layer build, has up to almost 300 microns of powder over the part as it's being printed. We can look at short feeds and so on and so forth. Now, what this is allowing for is that identification of anomalies, but also that decision making for as it goes. So what I kind of showed before with the anomalies is as we're detecting coda streaks, we can make different changes. Now, kind of as we look at this, I want to make a really clear kind of piece to it. As you're measuring your build, you always want to look at what is your certification part, what went perfectly, or what happened in the last build and how does this change? So we do have the ability here to measure and identify different anomalies for different builds and compare them side by side. So this is our compare feature where this is the same build on the same machine. And let's link these two together. So we're looking at the same things. So we're looking at the same build on the same machine where you're seeing different anomalies, different anomaly patterns, even if we wanted to go to a layer where in this part, there's some serious problems. We aren't really seeing an impact in this region as great as what was happening on the leading edge. And we can go through different examples here to see what was the problem within each region, and then what really happens as there is an impact or anomalies happening. This is what allows us to do quick comparison and quick analysis. The final piece to this, and I don't actually have any additional data loaded today, but we also have a feature that can add in any other data stream that you have. So if you have OT system, let's say for the EOS OT system, you can load in that data and compare them as a data stack. We can also add in any additional data streams into Fringe Operator, and this allows us to get a full end picture. Some of this work is also downloading CT data, so you can run a quick analysis and a side-by-side comparison. Once you have it loaded in, there's just a reference measurement that you can then load it in. It's relatively easy. One final piece to note before I kind of move to Fringe qualification here is this is loaded in real time. So as you are gathering the data in the build, Fringe Operator is loading the latest data in real time. Everything is stored locally, so there's no up to the cloud. The data is processed locally as well as able to identify anomalies. So this really is what's changing the industry and for our customers to be able to know what's happening. Now let's take a step back and see what's happening really over trends. So we've developed and released Fringe Qualification. Fringe Qualification is a tool where you're able to understand from every single machine that you're gathering data on and trends over time. So here we're looking at a data set where you can see different trends as builds are failing more. You can then take a deeper dive analysis to see success rate, how it has changed over time, looking at the anomalies over each build, as well as really what happens and what's the most important thing, how much money did you waste last year? This is a key piece for every single customer and everyone's management who wants to know how much money did I waste at the end of the day. Now, there are a lot of calculators built behind this to be able to quantify these figures, but what really it comes down to is the anomalies that passed or failed. Because if we really want to look, let's be realistic here, not every machine acts the same. So you can categorize it depending on the machine that you're running to be able to gather the data, see how the trends are. Maybe this machine needed new maintenance. Maybe it was the material itself, where your material, whether it's the Inconel, as it was growing, failure rates continued to change. This is critical so that you can really have that, hey, what happened over the last year? Let's look and understand from a high level perspective. We can also always dive into live builds, being able to understand and see the heartbeat chart for what's occurring as the anomalies change, as the anomalies or thresholds change. And this is what allows you to make those decisions from a high level. This is a tool that we see as being able to be on a screen at a manufacturing site so you can know what's happening. And then, as we kind of said, take a deeper dive into Fringe Operator for your engineers who know the technology well. And the final piece here is we need really, once we take an understanding of what's happening in the build, let's look at trends over time, still comparing them from one machine to another and tracking pass or fail criteria. This tool is really that part of your process so that you can understand what's happening over the entire value stream for your technology. Now, with this kind of understanding different anomalies, how it changes over time, we want to both thank you all for your time. I know we kind of ran through this. We can talk about Fringe Inspection for days. It's literally my job. So I'm going to open it up to questions. If anything else is missing, please let me know. And yeah, thank you all for the time. Really appreciate it.
All right, great. Ben, Noah, thank you very much for that great presentation highlighting Phase3D's capabilities. We're now going to head into the Q&A session. So if you do have questions, I've got some reports that maybe the Q&A isn't working for everybody. So if you want to go ahead and put your questions in the chat, you can do that and I can ask them. Or if you'd like to raise your hand and come off mute and ask directly, that's an option as well. So let's go ahead and get started on Q&A. Right, I have a quick one here, just to get us started. So let's see. So what is the process for installing Fringe Inspection at a facility? Is that a big undertaking?
Yeah, good question, Jason. So we didn't really note on this too much. Our technology, what we say today is it's about 24 hours, calendar hours of downtime. So we show up at noon, our technology is installed really in about 2 hours. And then through our calibration process, we make sure everything is settled and heat the build chamber overnight. And then in the morning, we're running our final calibration build. And that's really where we begin to train everyone who's at the facility as well. So typically show up at noon with lunch, leave at the next day lunch with everyone trained, and then we're always there. But it's a really easy process for removing screws and then or ports and then adding our technology on.
Very nice, thank you. All right, we have another one come in. Oh, have you installed your system on any other machines besides an EOS?
Yes, our technology is really machine agnostic. So we need those two things, a location, or really three, a location for a projector, a location for the camera system, and then a way to take the measurement or time when the measurement should be taken. So we've done on EOS, DMG, GE or equilibrium additive. We also do part of this work is, or our work has also been on binder jetting. So we've done work on the Innovent system, a Renishaw system, and then as well, right now we're working on a lot of other installations. So for most of the companies that you know of, we are probably working on an install right now for them. And we'll, follow us on LinkedIn to see as they come out.
All right, great, thank you. Let's see. Follow on. What backend permissions do you need to install your software?
Backend. Is that
I
question for
can take that one if you want.
Yeah, go for it, Ben.
So the way that the system is configured from a retrofit perspective is that all of the software operates off our own supplied PC that sits next to the machine. And so actually the system is completely separate to the AM machine. We're using a series of sensors to trigger when we take measurements in that retrofit scenario. We do work with some of the machine OEMs to integrate where we take triggers from their machine or and use some of their software capability, but our base product is completely standalone and the machine doesn't even know it's there.
Very nice. All right, so let's see. I don't see any other questions coming in.
I got a question.
There you go. Okay, we have a couple hands up. So Dean, you want to go ahead and then we'll follow up with Jim.
Hey, Noah, Ben, good presentation.
Hey,
Have you guys deployed your technology on any type of polymer melt extrusion machines?
Not to date, no.
Could you?
In terms of powder bed?
No, in terms of filament, measuring the height of each layer?
No, I mean, no, but we have a variant of our technology that we've used on cold spray systems, which could potentially be used in that area. Yeah. So the software is configured slightly differently because the head is moving on the cold spray system, but there's no reason. We really focused on metals and powder bed initially because it's where the biggest value proposition was in terms of end use. But if you have an application, we'd be more than happy to look at it.
And one more question. What's the approximate cost of adding your technology to a process? Give me a range.
Yeah, so depending on the size of the system and the resolution that is needed, it can range from between $45,000 to $100,000 in the first year, and then so a standard EOS M290 would be around that $45,000 to $50,000 mark, and then there's an ongoing license subscription depending on how many seats you have and how many people in your facility need access to the software.
Okay, great. Thanks.
All right. Thanks,
Thank you,
Dean.
Dean.
Jim, you want to go ahead and ask your question?
Yeah, actually, Ben, no, a nice presentation. Thank you very much. I had a similar question as Dean that you just answered. I was curious on, is it a monthly subscription fee to access the software and overall pricing? So I appreciate the response. Thanks.
Right. Let's see. Do you have any case studies that you can share in terms of cost savings that have resulted from using the tool and the software?
I mean, as you can probably appreciate, many of our customers are quite tight-lipped on their costs of how much they're spending on producing components and how much but we do have case studies available on our website that show the data that we've collected and how they were able to correlate that to defects in their parts. Yeah, I mean, this is challenging because what defects people can accept is a big challenge for us. Everybody has some different specifications. So if I give you an example, we have some customers that say, so long as there isn't a pore over a couple of millimeters, then we're good. And we have other customers that say, we can accept pores up to 100 microns, and we can accept an amount of pores between 100 and 250, but over 250, we've got an issue. So there's a real, it really does mean understanding, us working with you, our applications engineers, understanding what your qualification criteria is and developing out, the studies to say, okay, how often is this happening in your production environment with the parts that you're trying to build, right? But yes, there are case studies on the website, and if you want to send your contact details, we can send you links to those as well.
All right, great. Thank you. Just a couple more here. First off, nice presentation. Can your tool estimate anomaly size and output to a data file?
Yes. So our core technology, Fringe Inspection, the data output itself, is as you're identifying anomalies, there's actually it's not a text file, but I don't remember the exact data format, where it's categorizing and
A map file.
Yeah, so it's not only the map file, which is your height map data, but it's also a text file that's basically saying, like I view it as a text file. It's saying where the anomalies are for which layer. Also, this is able to get imported into a report feature that we have, and that is what you can then take for your certification process, pass it on to your QA engineers. And that also depends on your anomalies, the anomaly size that you want to detect, so that you can look at, if you only want to see things over 100 micron anomalies in X and Y and Z over 50 microns, you can all program that in so it gets exported as a text file or a report. It's very configurable.
Great, thank you. So it sounds like there's a couple different options for reports. All right, so one more here. Does camera calibration heighten the process parameters and material? Let's see, if for an alloy process parameters, including laser spot size change, does it mean the calibration needs to be repeated?
So I can take this one now. So not the calibration doesn't need to be repeated. However, if you're switching from material to material inside the machine, there are some settings that will change in terms of the intensity of the projection and the exposure of the camera, just because the reflectivity of different powders. We don't want to oversaturate images, so we control or we change the parameters based on what material you're running. But because we're not really doing anything to do with the laser, right? We're taking the measurement after the process has finished scanning or after the layer has been done. Individual process parameter changes don't affect our calibration.
All right, great. Thank you very much, gentlemen. All right, so that's all the questions I see. No other hands raised. So I guess that'll wrap up today's NCDMM Alliance Partner Lunch and Learn. I would like to just thank once again Ben and Noah, and also Phase3D. It was a great presentation. And if you have further questions for them, please reach out directly at the emails on the screen. They have their contact information on the screen. This presentation will be shared on the website and also on the YouTube page. So if you want to go ahead and check it out, you can check it out there. And I will once again share the chat share the link in the chat if you are interested in becoming an NCDM Alliance partner. Go ahead and follow that chat and fill out the form. We'll contact you. So yeah, thanks again, everyone, for joining the NCDM Alliance Partner Lunch and Learn. And everyone have a great afternoon.
Thank
you
you
all.
all.
Thanks, guys.